What if the most subtle fact you have ever learned is actually the biggest illusion? You wake up, check your phone, time moves forward, always the same rhythm, and you accept it because, well, that is just how the universe works. But here is the problem. Physics as we know it has an open door, a mathematical crack that suggests the steady flow of time might not be the whole story. This isn't fantasy, it is a serious puzzle hidden inside our deepest theories. If time is so firm, why does a single equation allow it to bend, twist, and loop back on itself? And what happens to our logic when that loop contradicts everything we assume, creating a paradox that seems impossible to resolve? So we accept that time flows, that cause always precedes effect. But what if that arrow could bend backward, creating a loop so tight it destroys its own starting point? This is the heart of the grandfather paradox, a logical puzzle that has haunted physics and philosophy for decades. The scenario is brutally simple. You travel back in time and kill your own grandfather before he has children. Your parent is never born, so you are never born, so you could never have traveled back in time to commit the act. This creates a self-destructing contradiction, a loop that rips a hole in our understanding of causality. The French science fiction writer René Barjavel brought this idea into the mainstream with his 1944 novel Le Voyageur Imprudent, where a soldier travels back and murders his ancestor. The problem isn't just about human action, it cuts to the core of our physical laws. If you could prevent your parents from ever meeting, your own existence would be erased, and the energy and matter that make up your body would never have been arranged into a conscious traveler. This suggests that backward time travel might violate some of our most cherished principles, including the conservation of energy and the relentless march of entropy, as noted by the Stanford Encyclopedia of Philosophy. To truly grasp the paradox, let's break it down into 5 simple steps. First, establish the basic rule of causality that an effect cannot precede its cause. Second, imagine 2 separate timelines, the normal flow of history and the personal journey of the traveler. Third, trace the chain. The traveler is born, he journeys back, he kills his grandfather, and therefore he is never born. Fourth, you'll find the contradiction. The traveler's existence is a logical impossibility because his actions in the past erase his own reason for being. And finally, you're left with only 3 possible escape hatches. Either the universe branches into multiple realities, history creates a perfectly consistent loop where your actions were always part of the story, or nature itself finds a way to block the action from ever happening. These are the only logical resolutions. Interestingly, the physicist Stephen Hawking was famously skeptical, once dryly noting that if time travel were possible, we would have already been overrun by tourists from the future. Kip Thorne, who would later design the physics for Christopher Nolan's film Interstellar, was initially so opposed to the idea that he only began serious research after a determined graduate student, Ulf, convinced him to consider exotic matter. He went from outright dismissal to becoming a central figure in the field. So now we are left with the most pressing question. Could there be a set of mathematical equations, a perfect and elegant solution, that would make this impossible loop legal within the laws of physics? Kurt Gödel was Albert Einstein's closest friend at Princeton, and the two walked home together almost every day. In 1949, this celebrated mathematician handed Einstein a solution that shook the very foundation of physics. Gödel had solved Einstein's own field equations from general relativity, but his answer described a universe that rotated. In that rotating cosmos, space and time twisted so severely that the fabric itself curled into loops. These are called closed time-like curves, and they are essentially paths that return to their exact starting point in time. Mathematically, this meant a person could travel into the past without violating a single equation that Einstein had written. The mathematics was flawless, yet the implication was so disturbing that even the father of relativity felt deeply unsettled. Einstein reportedly admitted that the results seemed to bother him, a rare crack in his usual calm confidence. He could not find a flaw in Gödel's reasoning, yet his intuition rebelled against the idea of time travel. The problem was that Gödel's universe demanded a very specific condition. All matter had to rotate uniformly around a single axis. Modern observations of the cosmic microwave background radiation have since completely ruled out that scenario. Our universe simply does not spin in the way Gödel's solution required, and without that rotation, his time machines cannot exist. So the first serious attempt to legitimize time travel collapsed under the weight of astronomical evidence. Here is where the story takes a darker turn. When Stephen Hawking was once asked if he believed in the possibility of traveling back in time, he gave a famously dry response. He said that if it were possible, we would already have been overrun by tourists from the future. That quip captured a profound logical tension that no mathematician had yet resolved. Gödel showed that the equations could allow time travel, Einstein felt the discomfort, and Hawking sharpened the paradox into a single, mocking sentence. But the door was now open, and a young physicist named Kip Thorne was about to walk through it. The question was no longer whether time travel could exist in some exotic universe, but whether it could exist in ours. For most of his career, Kip Thorne refused to take the idea of time travel seriously. It took a persistent graduate student, now known as Ulvi Yurtsever, to convince him that exotic matter might make it possible. That shift turned Thorne into a central figure in the field, eventually leading him to serve as the science advisor for Christopher Nolan's Interstellar. In 2014, he designed the wormhole and black hole in that film using actual physics equations, even accounting for time dilation on Miller's planet. Before that, in 1988, Thorne and his Caltech colleagues Michael Morris and Ulvi Yurtsever published a groundbreaking paper in Physical Review Letters. The paper, Wormholes, Time Machines and the Weak Energy Condition, proposed that exotic matter could keep a wormhole open for time travel. A wormhole is a theoretical tunnel connecting two distant points in space and time. Normally, gravity would crush such a tunnel instantly, but exotic matter with negative energy could counteract that collapse. So, the dream is that you step into one mouth and exit through the other at a different point in history. Before you get excited, let's learn how to judge such research yourself. Start by checking if the work mentions closed time-like curves or CTCs, because without them, it is not real time travel. Next, determine whether the conclusion comes from pure mathematics or from actual experiments. Then, read the limitations section carefully to spot assumptions like needing negative energy. Finally, verify that the work passed peer review, since without expert scrutiny, it remains unconfirmed. This method is drawn from the review guidelines of physical review journals, which have shaped physics research for over a century. Thorne's wormhole idea meets all four criteria, but it demands something we have never observed on a large scale. The paper was mathematically sound, yet it relied on a substance that may not exist in sufficient quantity. Still, the notion of using a cosmic shortcut to violate causality was suddenly a serious scientific topic. That brings us to the one ingredient that makes or breaks the whole plan, the mysterious exotic matter. So the wormhole exists on paper, but there is a catch that makes every physicist wince. To keep the throat open, you cannot use ordinary matter because gravity always wants to crush it shut. You need something with negative energy density, a substance so strange it bends space-time in the opposite direction, pushing the walls apart instead of pulling them together. This is what physicists call exotic matter. And here is the brutal part. We have never observed it on any macroscopic scale in nature. It is not like finding a new element or a rare rock. It is a category of stuff that seems to violate every rule we know about how energy should behave. Think about the difference this way. Normal matter, the chair you sit on, the air you breathe, always has positive energy, and positive energy always pulls things together. Exotic matter, if it exists, carries negative energy, and negative energy would act like anti-gravity, repelling everything around it. According to Caltech's research on Kip Thorne's model, you would need a chunk of this material so massive that it could hold an opening wide enough for a human to pass through. And that requirement alone pushes the idea into the realm of fantasy. But then quantum mechanics steps in and whispers something strange. Negative energy might not be entirely impossible. The Heisenberg uncertainty principle, one of the strangest ideas in physics, says that empty space is not truly empty. It is a boiling sea of particles that constantly pop into existence and vanish, borrowing energy from nowhere for absurdly short moments. In 1997, a physicist named Lamoureux proved this with the Casimir effect, placing two metal plates incredibly close together and measuring a tiny attractive force between them. That force comes from negative energy in the vacuum, real, measurable, and utterly bizarre, but the amount is unbelievably small, enough for microscopic effects, nowhere near enough to hold a wormhole open for a traveler. So where does that leave us? Here is where a group of students at the University of Bristol did something in 2019 that turned heads. They used a quantum algorithm to simulate reversing time for a single electron, not physically sending it backward, but mathematically processing its state so the result looked identical to its starting point. They published their work in Physical Review A, and the global media went wild, calling it a step closer to retrocausality. But be honest about the scale: one photon, one simulation, no actual journey through time. It is a whisper of what might be possible, not a demonstration that the universe bends to our will. And yet that whisper is enough to keep the question alive, because if quantum mechanics permits negative energy at the smallest scale, maybe, just maybe, the universe has a loophole we have not yet learned to exploit. So what happens if we refuse to accept that a paradox can destroy the very possibility of time travel? What if the universe has a loophole so strange that it turns a logical dead end into a doorway? This is where quantum mechanics steps in, and it brings a solution so radical that it feels like science fiction, even to physicists. Picture this. You travel back in time, you find your grandfather, and you pull the trigger. In a normal universe, that action should erase your own existence. But in the many worlds interpretation, the moment you arrive in the past, you don't just enter one timeline, you enter an infinite branching of them. The gun fires, your grandfather dies, but you don't vanish. Instead, you have simply killed the grandfather of a different version of you, a copy living in a parallel branch of reality. Your own timeline remains perfectly intact, because you never actually belonged to that past in the first place. This is the escape hatch proposed by physicist Max Tegmark, who introduced the idea in a 1997 paper in Foundations of Physics Letters. He called it quantum suicide and its counterpart, quantum immortality. His argument is simple. In an infinite multiverse, every possible outcome happens somewhere. So when you try to kill your grandfather, there will always be at least one branch of reality where the gun jams, or your hand shakes, or he simply moves out of the way. And that is the only branch where your conscious self continues to exist. Every other version of you may have succeeded, but you will never know, because you are only aware of the timeline where you survived. The paradox doesn't disappear, it just becomes irrelevant, because you are always following the path where it fails. David Deutsch, a physicist at Oxford, pushed this idea even further. In a 2014 interview with the New York Times, he explained that if the universe is truly infinite, then there are countless copies of you, countless versions of your grandfather, and countless pasts where slightly different histories have unfolded. Traveling back in time in this view is not about altering your own past at all. It is simply a matter of moving sideways into a branch where the past is already different. You never change history, you just choose a different one. There is no contradiction, because you were never supposed to be part of that other timeline in the first place. Now compare that to an earlier idea from the philosopher David Lewis. In his 1976 essay, The Paradoxes of Time Travel, published in American Philosophical Quarterly, he argued that the whole paradox is a misunderstanding. If you travel back in time and kill your grandfather, then you have always killed your grandfather, and you have always existed anyway, because your action is part of the history that led to your birth in some other way. It sounds impossible, but Lewis insisted it is not a contradiction, it is just a strange fact about a world where time is not a simple line. His model keeps everything in one timeline, but it forces you to accept that your actions in the past are fixed, predetermined, and utterly incapable of changing anything. Deutsch's multiverse, on the other hand, sets you free. You are not trapped in a fixed history, you simply slip into another one. So which one is true? Here is the punchline that changes everything. If Deutsch is right, then the moment you step into a time machine, you are not going back to your past. You are going to a past that belongs to someone else, somewhere else. You are not a time traveler. You are a universe traveler, and the grandfather you meet was never yours to begin with. This means the paradox is not solved, it is completely dissolved, because the question was never about logic, it was about identity. What if your freedom to act in the past is an illusion, not because of a physical law, but because of a logical one? This is the unsettling claim at the heart of the Novikov self-consistency principle. Named after the Russian physicist Igor Novikov, who developed it with Kip Thorne in 1990, this idea suggests that the universe simply will not allow a paradox to form. The laws of physics will conspire to ensure that any action you take in the past was always a part of history. You could travel back to meet your grandfather, but some force, a flat tire, a sudden change of heart, would always prevent you from harming him. Your journey is not a contradiction, it is a completion of existing events. Every step you take was already woven into the fabric of what has always been. The principle reframes the entire problem with a disarmingly simple premise. Causality is inviolable, and therefore time travel is inherently self-correcting. It does not restrict your ability to choose. It just dictates that your choices will only ever align with a timeline that already includes you. You possess complete freedom to act, yet you are fundamentally incapable of altering the sequence of events that led to your own existence. A bullet fired at your grandfather would always be a dud, or perhaps you would simply miss. This notion suggests that the past is not a fragile structure that can be broken, but a rigid, deterministic tapestry that you become a part of, not an agent of change. Physicist Carlo Rovelli offers a profound and personal perspective on why this might be the case. In a 2018 interview with The Guardian, he recounted a recurring dream of a relentless rain and a clock with no hands, a vision he credits with helping him abandon his belief in time as a fundamental reality. This philosophical shift led him to develop loop quantum gravity, a theory where time does not exist at the most basic level of reality. Instead, the universe is a network of interconnected events, a static web where the past, present, and future are not distinct domains but part of a single unified picture. From this view, the whole idea of traveling back becomes nonsensical, because there is no singular flowing timeline to travel along. This concept is further reinforced by the mathematics itself, as the variable for time famously disappears from the Wheeler-DeWitt equation, a cornerstone of quantum gravity. In this framework, the universe is not a story that unfolds but a frozen landscape, and our perception of time's passage is merely an illusion born from our limited perspective. If this is the true nature of reality, then a time machine does not need to circumvent physical barriers. It would have to contradict the very foundation of existence. So, we are left with a choice between a universe that actively prevents you from changing anything and a universe where the question is perhaps meaningless to ask. Is this rigid consistency the final word, or can we find a crack in the fabric of space-time itself? Time travel often feels like an idea reserved for fiction, a convenient plot device for movies and novels. But what if the universe itself provides the blueprint for such machines on a scale that defies all imagination? We have already explored wormholes, yet those theoretical tunnels might not be the only cosmic loopholes available to us. Physicists have proposed other structures that could warp space-time into a closed loop, allowing a path back to yesterday. One of the most intriguing proposals came from Richard Gott at Princeton in 1991, involving objects called cosmic strings, which are essentially incredibly dense defects in the fabric of space-time itself. According to his calculations, if you could bring two of these cosmic strings together at incredibly high speeds, they might twist space-time enough to create a closed time-like curve. But here is the catch that makes this solution feel almost insulting to our ambitions. The process would require the total energy output of an entire galaxy, a resource that is simply not available to us. In 1995, Gott took this idea further and calculated that to build a cosmic string long enough for time travel, you would need an object with a mass about 10 quadrillion times that of our Sun. That is heavier than the combined mass of entire clusters of galaxies, an object so colossal that it defies any practical engineering concept we possess. So while the mathematics might be elegant, the cosmic string approach remains a purely theoretical exercise, a monument to the gap between what is possible and what is attainable. This brings us to another exotic option, the rotating black hole, a solution to Einstein's field equations that seems to offer a secret passage inside its event horizon. The mathematics suggest that a Kerr black hole might not lead to a singularity, but instead to a tunnel that could connect to another part of space-time. Yet recent research paints a far more violent picture, showing that any matter entering this rotating giant would be destroyed by immense radiation and tidal forces long before reaching any potential gateway. The sheer scale of these cosmic machines highlights a fundamental truth. Even if physics permits time travel, the universe's architecture seems almost deliberately designed to keep it out of our reach. Imagine a decision you make right now, in this present moment, somehow reaching back and altering a photon state years before you were even born. That sounds like pure science fiction, yet it is precisely the kind of result that emerged from a landmark physics experiment in 1999. At the University of Maryland, a team led by Yoon-Ho Kim used a setup known as the delayed choice quantum eraser to probe the strange behavior of light. Their work suggested that a measurement performed now could influence the past behavior of a particle, blurring the line between cause and effect at the most fundamental level. Building on this curious foundation, physicist John Cramer offered a startling interpretation of those statistical results. In 2003, he proposed that photons might actually send information backward in time to select their own initial state, creating a tiny loop of retrocausality. It was a mathematically consistent story, but definitively proving such a bizarre notion in the lab remains a monumental challenge. Beyond single particles, the arrow of time itself appears to be fragile when the universe gets very small. A study published in Nature Physics in 2021, carried out by researchers at ETH Zurich, demonstrated that the forward flow of entropy could be reversed in a quantum system containing fewer than 10 particles. This gives us a glimpse of a microscopic realm where time's direction is not a fixed rule but a statistical probability. Even more astonishing, experiments at CERN with the Large Hadron Collider have revealed that the subatomic world has a built-in asymmetry. By observing the behavior of particles like pions and kaons, scientists found a tiny violation of a fundamental symmetry known as CPT at a rate of about 0.2%. The implication is that the universe itself does not treat the past and the future with perfect equality, adding another layer of complexity to our understanding. Now, you might be wondering if these incredible effects mean that time travel is actually happening all around us. To help you separate fact from fiction, let's break down how to view these discoveries with a clear scientific mind. First, recognize that the classic absolute time you see in older movies is simply a myth that science has abandoned. Second, pay attention to how films handle relativity. If a movie like Interstellar shows time slowing down near a massive object, that part is rooted in real physics. Next, keep this simple distinction in mind. Physics allows for limited travel into the future, but a trip back in time remains a much more questionable possibility. Finally, ask yourself a crucial question about any time travel story. Where exactly would a traveler exist between the two bridged moments in space-time? If the story cannot offer a plausible answer to this, it is likely taking a huge leap into fantasy. So, while we cannot yet build a machine to visit our ancestors, these experiments reveal a truth that is far more bizarre. The universe at its smallest scales operates under rules that defy our everyday logic and challenge our very concept of history. Back in 1902, a group of Cambridge students founded a society called the Time Travelers Club, yet it had just 4 members and never actually held a single meeting, which remains a wonderfully strange footnote in the archives of history today. It seems the idea of journeying through the ages has always captured our imagination, even if we are not quite sure what to do with it. According to a YouGov survey from 2022, 27% of Americans believe time travel is scientifically possible in the future, and 12% even suspect it has been secretly attempted already. But walling off the laboratory does not stop the dreamers from trying, because every year, the editors of Physics Today receive roughly 200 papers claiming someone has invented a time machine or reversed entropy. These submissions come almost entirely from amateur inventors, and not a single one has passed peer review. Yet the sheer volume of them tells you something profound about our species. We are so drawn to the promise of bending time that entire folklore traditions have built up around it. From the Philadelphia experiment in 1943 to the Montauk Project decades later, which allegedly saw the US military conduct secret tests. Most scientists dismiss those stories as urban legends, a verdict that never stops them from circulating in best-selling books like David Hatcher Childress's The Time Travel Handbook. Still, maybe the future is not about bulky machines at all, because researchers like David Deutsch and Seth Lloyd have proposed something called quantum navigation, a way for computer systems to predict their own state so precisely that they choose the perfect path without moving backward. Is it time travel, or just a smarter way of seeing what is already coming? Before we get lost in the potential of these ideas, let us step back to ask why time seems so determined to flow in only one direction. Why does time flow in one direction at all? The deepest answer, according to physicist Sean Carroll at Caltech in his book, The Big Picture, comes down to entropy, though the microscopic equations of physics are perfectly symmetric with time. As Carroll explains, this asymmetry only emerges at the macroscopic scale, where you are dealing with something like 10 to the 23rd particles or more, and at that scale, the universe simply refuses to run in reverse. Remarkably, this strange relativity of time has everyday consequences that our technology must constantly correct for. At the moon's distance, time according to special relativity runs about 2.5 milliseconds slower per year than it does on Earth. Yet the gravitational pull of our planet causes the exact opposite effect, making lunar time run slightly faster. This small but measurable discrepancy has to be accounted for in GPS satellites and atomic clocks. Otherwise, our navigation systems would drift out of sync within days, which is just one proof that our one-way experience of time is not as universal as it feels. Some physicists suggest we are simply asking the wrong kind of question. Michio Kaku, one of the most prominent popularizers of science, has described time travel as a pure engineering problem rather than a scientific one, arguing that we do not need to discover a new law of physics, we just need to master the technology we already understand. According to that view, the blockade is not a wall of impossibility, but merely a mountain of practical difficulty, though the mountain may be far taller than we can climb. The real danger might lie in what happens to the fabric of reality itself. Jim Al-Khalili, a quantum physicist at the University of Surrey, warns that the greatest threat of time travel is the loss of uniqueness, meaning that if you ever managed to create a closed time-like curve, quantum effects would pile up so chaotically that the universe would collapse into a state that no calculation could ever predict. In that scenario, a single trip backward would not rewrite history, it would unravel everything in a kind of thermal death, where cause and effect lose all meaning. Some modern theories push this even further, suggesting that time itself might be nothing more than an illusion constructed by our limited perspective. The Wheeler-DeWitt equation, a foundational tool in quantum gravity, famously eliminates the time variable altogether, leaving only a static of interconnected events with no privileged arrow pointing forward. If that mathematical framework is correct, then our entire sense of past, present, and future is a human invention. And the question of traveling backward through time becomes as meaningless as asking which direction is north on a sphere. So, if time is just a stage we have built for ourselves, what would it even mean to step off it? And would there be anything waiting for us on the other side? So, we began with a question about the possibility of time travel, about whether the river of time could ever flow backward. We have walked through the paradoxes that baffle our logic and the elegant mathematics that seem to permit the impossible. We have seen how closed time-like curves emerge from spinning universes, how wormholes could be held open by impossible matter, and how quantum mechanics might offer an escape through branching realities. We have confronted the stubborn arrow of entropy, the fundamental reason why our universe remembers the past but not the future. Every path, from the grandest cosmic strings to the most delicate quantum experiments, seems to lead to the same gate, a barrier we lack the technology, the energy, or perhaps the very understanding to open. Yet, does our inability to build a machine mean the question itself is without value? These explorations are not failures. They are maps of the boundary of human knowledge drawn by some of the finest minds across decades. The limitations we face do not extinguish our curiosity. They illuminate how much remains unknown. Perhaps the true journey is not about bending space-time to our will, but about understanding our place within its grand, indifferent architecture. We race along this one-way current, and maybe the greatest wonder is not returning to the past, but arriving at this very moment, here and now. So what does it mean for you? Standing on this edge of the known, feeling time pull you forward.